Right now, there's a spacecraft screaming through empty space. It is 24 billion kilometers from Earth. To put that in perspective, if you drove there at highway speed, it would take you approximately 25,000 years to arrive. And the transmitter keeping Voyager probes alive? It runs on roughly the same power as the light bulb inside your refrigerator. That little bulb. And yet, NASA is still talking to it, receiving live data, sending software updates, having a two-way conversation across the largest distance any human-made object has ever traveled. So how? How is this even remotely possible? How do you maintain a phone call with a machine that left our solar system, that literally crossed the boundary of everything the sun controls, and is now drifting through interstellar space? That's what we're going to find out today. Let's go back to 1964. A graduate student, Gary Flandreau at NASA's Jet Propulsion Laboratory, is doing what grad students do, staring at numbers, running calculations, probably exhausted, probably underpaid. And then he sees something in the math that makes him stop. A planetary alignment. One that only happens once every 176 years. Jupiter, Saturn, Uranus, and Neptune, all four outer planets, lined up so perfectly that a single spacecraft could slingshot between all of them. Use each planet's gravity like a catapult. Swing from one to the next without burning barely any fuel. A trip that would normally take 30 years could be done in 12. NASA loved it. They called it the Grand Tour. They planned 4 spacecraft. They were going all in. Then the Apollo program ended. Budgets got slashed. The space shuttle became the priority. And the Grand Tour got gutted down to just 2 probes. Voyager 1 and Voyager 2. Voyager 2 launched first, August 20th, 1977, on a slower trajectory designed to visit all 4 planets. Voyager 1 followed on September 5th, on a faster path aimed at Jupiter and Saturn. Here's the thing about the outer solar system in 1977. We didn't really know what was out there. We had telescopes. We had theories. But we had never actually been there. Voyager changed that overnight. When Voyager 1 flew past Jupiter, it sent back something nobody expected: active volcanoes on Io, one of Jupiter's moons. Scientists saw the images and genuinely couldn't believe what they were looking at: a moon with erupting volcanoes. Io is the most geologically active object in the entire solar system, and we had zero idea until Voyager flew right past it. Saturn's rings, which we'd always seen as smooth bands from Earth, up close, they turned out to be thousands of individual rings. Some braided, some twisted, some with shepherd moons, herding the particles into lanes. The complexity was mind-bending, and Voyager 2 kept going. Past Uranus, past Neptune. It became, and still remains, the only spacecraft in human history to visit those 2 planets. No mission has gone back. What we know about Uranus and Neptune is largely what Voyager 2 told us from a single flyby decades ago. Then came the moment Carl Sagan pushed for, a photograph that became one of the most iconic images ever taken. February 14th, 1990, Valentine's Day. Voyager 1 had long since completed its planetary mission and was heading out of the solar system. Scientists turned its camera around, one final look back, and captured a photo of Earth from 6 billion kilometers away. Earth appeared as a pale blue dot, less than a single pixel, suspended in a beam of scattered sunlight. Then Voyager 1 turned its camera off forever and kept flying. Outward, into the dark. Okay, here's where it gets genuinely insane. Voyager 1's antenna is 3.7 meters wide. Looks impressive. But the transmitter powering it produces about 22 watts of power. That's your refrigerator light bulb. That's less power than a standard laptop charger. and that signal has to travel 24 billion kilometers to reach us. By the time it arrives on Earth, it has lost almost everything. The signal lands at less than 1 attowatt. We're talking about a billionth of a watt. That is 20 billion times weaker than the battery in a digital watch. So how do we hear it? NASA built the Deep Space Network. 3 massive antenna complexes positioned around the world. One in the Mojave Desert in California, one outside Madrid in Spain, one outside Canberra in Australia, spaced roughly 120 degrees apart so that as the Earth rotates, at least one station always has line of sight to deep space. The dishes are enormous, 70 meters across, and the receivers are cooled to within 4 degrees of absolute zero. That's colder than the surface of Pluto. They have to be that cold because at these sensitivity levels, even the faint warmth of the electronics themselves would create too much noise to hear Voyager's signal. And even with all of that, even with the giant dishes and the cryogenic cooling, the signal is so faint and Voyager is moving so fast that its signal gets Doppler shifted. The same effect that stretches light from distant galaxies is stretching Voyager's radio waves. The team has to calculate and compensate for that shift in real time just to decode what the spacecraft is saying. But here's what most people don't know. We have almost lost both Voyagers. Multiple times. In 1978. 8 months after launch, someone on the ground made a scheduling error. Voyager 2 didn't hear from Earth for 7 days. Its software panicked, assumed the primary receiver had failed, and switched to the backup. The backup had a broken capacitor. It couldn't properly lock onto Earth's signal. When engineers tried to switch back to the primary receiver, it was dead, completely fried. Voyager 2 was stranded 8 months into its mission, communicating through a busted backup receiver that could barely hear them. The team in Madrid started sweeping through frequencies, slowly, painstakingly, searching for the exact input that the broken receiver could hear. Hours of trial and error from hundreds of millions of kilometers away. And eventually, Voyager 2 phoned home. That workaround they rigged together in 1978? That's how Voyager 2 has been communicating ever since. Nearly 50 years on a jerry-rigged backup. It never got fixed. It couldn't be. So the engineers just adapted and kept going. And in 2020, Voyager 2 was doing a routine calibration roll when a command delay caused 2 power-hungry systems to run simultaneously. The spacecraft drew more power than it had available. Its safety software instantly shut down all 5 remaining science instruments to prevent catastrophic failure. It took a week to fix because every message took 17 hours to reach Voyager 2 and 17 hours to receive a reply. One mistake, a week to undo it, and in 2022, Voyager 1 started sending back gibberish, pure, random-looking data. No one could figure out what was happening. Eventually, they traced it. Voyager had somehow started routing its data through a computer that hadn't worked in years. A dead computer. Just garbling everything before it reached the transmitter. The fix sounds simple. Tell it to use the right computer from 24 billion kilometers away with a 23-hour one-way signal delay, using 1970s hardware running on less memory than a car key fob. They fixed it. Here's the part that hits different when you really think about it. The entire team responsible for keeping both Voyagers alive? Only 10 people. 10 people. 2 spacecraft beyond the solar system. 50 years of mission. And every single time something has broken on hardware that was built in the 1970s. That was designed for a 5-year mission. That is now 48 years old. That no one can physically touch or repair. This team has found a way. The computers on board? All 6 combined have 68 kilobytes of memory. Your phone has 2 million times more processing power. And NASA has been pushing software patches to these things for 5 decades. The power source is a set of nuclear batteries, radioisotope thermoelectric generators, powered by decaying plutonium. When Voyager launched, each probe had 470 watts. Today, they're down to about 210 watts, and it drops a little every year. Every year, the team has to decide which instrument to shut down, which sensor goes dark permanently, on a probe that's never coming home and that will never be replaced. The team estimates they have maybe 5 more years. By 2030, the power will be too low. The last instruments will go dark. The signal will fade below what the deep space network can detect, and then silence. But here's the thing. Silence doesn't mean stopped. Both Voyagers will keep flying. At 17 kilometers per second through interstellar space, with no friction to slow them down, they will travel essentially forever. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star in the constellation Camelopardalis. In 296,000 years, Voyager 2 will pass near Sirius, the brightest star in our night sky. They'll be out there long after the last human who remembers them is gone. This was just the beginning. Subscribe so you don't miss what's next. And if this blew your mind, subscribe and share it with someone who needs it.